In this lecture video, we're going to look at how to make inferences about a population total. Now, in many applications, it will be of interest to make inferences about the total of a population rather than the mean. Denote the population total by lowercase Greek letter tau. It is the sum of all capital N values in the population. So tau is equal to the sum, k going from 1 up to cap n, of the u sub k's. Remember that we're using the letter u to represent values in the population when we're looking at the entire population. Now, this can also be expressed as the size of the population times the population mean, mu. So we can represent the population total in either of these two ways. Now, an unbiased estimator of the population total is the scaled version of the sample total given by the following. So again, if we have a simple random sample of size little n from this finite population of size cap n, the values in the sample being represented by x's here, so the sample total is the sum, I going from 1 up to little n, of the x sub i's. And the unbiased estimator of the population total is the scaled up version of that sample total, the scale factor being the ratio of the population size to the sample size. Now, we can also calculate this unbiased estimator of the population total as the population size times the unbiased estimate of the population mean. So we can express this in either of these two ways. Now let's consider the variance and the standard error of the estimator of the population total. Under simple random sampling, the variance of the sampling distribution of the estimator of the population total is given by the following expression. So sigma squared sub tau hat, which is the notation for the variance of tau hat that we will use. We'll also use this notation, var, or variance of tau hat. The variance of the sampling distribution of tau hat is given by this expression. So it's equal to the square of the population size times cap n minus little n over cap n minus 1 times 1 over n, little n, times the population variance. Now, once we have this expression for the variance of the sampling distribution of tau hat, then we can take its square root to get the standard error of the estimator of the population total, or in other words, the standard error of tau hat. All right, so this is just cap n, the population size, times the square root of cap n minus little n divided by cap n minus 1, 1 over little n, times, and then you see out here, this sigma, this is outside of the square root sign. If we wanted to put that sigma inside, then we would have to make sure that it's squared. All right, so you see how you can we can express this standard error of tau hat in a couple different ways, depending upon how we simplify after we take the square root of the variance. Now, the problem is that we can't calculate either of these because they depend on the unknown value of sigma squared or sigma, depending upon which one of these you're looking at. And so we have to estimate the variance and the standard error by first estimating the population variance. Now, an unbiased estimator of the variance of the sampling distribution of the estimator of the population total, in other words, an unbiased estimator of the variance of tau hat, is given by plugging in the estimator for sigma squared and then simplifying. And so when we go through that simplification process, we can express this estimator of the variance of tau hat in terms of the sample variance s squared. All right, and so we see that this is equal to cap n times cap n minus little n over, or times 1 over little n times the sample variance. Once we have that, we obtain the corresponding estimator of the standard error of the estimator of the population total by taking the square root of that. And we see we can express this in a couple different ways depending upon whether we leave s squared under the square root sign or if we pull it out and take the square root in order to do that. So again, what we're doing here is expressing the estimated variance and the estimated standard error of tau hat in terms of the sample variance. Now, once we have the estimated standard error of tau hat, we can use that to come up with the margin of error for an approximate 95% confidence interval estimate of the population total. All right, and so this is the estimated margin of error for an approximate 95% confidence interval. So this is, in other words, this is the margin of error associated with tau hat. All right, so 2 times the estimated standard error of tau hat, or 2 times the square root of cap n times cap n minus 1 times 1 over little n times the sample standard deviation, which again is outside of the square root sign. So once we have this approximate 95% margin of error, then we can subtract that from and add that to our point estimate of the population total, tau hat, all right, to come up with our confidence interval. And so remember, we start off with our point estimate, tau hat, and then we go a distance to the left and a distance to the right from that point to get the endpoints of our interval. And that distance is the margin of error associated with the interval. All right, and so we see that that is twice the estimated standard error of tau hat. And so these are the formulas for the lower endpoint and the upper endpoint for that interval. All right, so let's look at an example. A firm is concerned about the time spent per week by employees on a certain administrative task. The time log sheets of a simple random sample of 50 employees showed an average amount of time spent of 10.31 hours with a sample variance of 2.25 hours squared. Now, the company has 750 employees. So what we want to do here is estimate the total number of man-hours spent on these administrative tasks and calculate the approximate margin of error associated with that estimate. All right, so we've got cap n equal to 750 employees in the company. We have selected a simple random sample of little n equal to 50 employees' timesheets. The sample mean number of hours spent on these particular administrative tasks is 10.31 hours. The sample variance of the data is 2.25 hours squared. Therefore, the sample standard deviation is 1.50 hours. The point estimate for the average, the population average number of hours spent by the 750 employees on these administrative tasks is 10.31 hours, which was X bar, right? That's our unbiased estimate of mu hat. And then we can use that to come up with our unbiased estimate of the total number of hours spent by all 750 employees on these tasks. So the total, and so we get that by multiplying this estimate of mu by cap n, the population size. And so that would give us 750 employees times 10.31 hours per employee. And so then we come up with 7,732.5 employee hours as our estimate, point estimate, for the total number of hours spent by folks in this company on these administrative tasks. And so you can see why the company may want to estimate the total rather than the mean, because then they can come up with, they can estimate how much money the company is spending or paying these employees to do these administrative tasks. Now, the approximate 95% margin of error associated with tau hat is 2 times the estimated standard error, all right, which is given by this formula here. And so we see here that that turns out to be 307.409 hours. Now, we can use that to come up with an approximate 95% confidence interval for the total number of hours spent by all 750 employees on these administrative tasks. And so we, again, start off with our point estimate, 7,732.5 hours, minus and plus 307.409 hours. And then once I get the endpoints, I can round them to, let's say, 2 decimal places, which I've done here. And so we can be 95% confident that the total number of hours spent on these certain administrative tasks is somewhere between 7,425.09 hours and 8,039.91 hours per week. All right, now moving on, let's look and see how to estimate a population total with a specified margin of error. So a simple random sample is to be selected from a finite population of size cap n with population mean mu, population variance sigma squared, and population total tau for the purpose of estimating the total of the population. This is a typo here. All right, so this should say total. So make sure that you correct that in your notes. Now, the sample size needed to estimate the total with an approximate 95% margin of error equal to some specified value, cap E, is given by this expression here. So the sample size required is 4 times the cube of the population size times the population variance divided by 4 times cap n squared times the population variance plus 1 less than the population size times the square of the desired margin of error. Now, note that this formula depends on the population variance, sigma squared, which will typically be unknown, and so it will either need to be estimated from prior studies or approximated in some other way, for example, perhaps using the empirical rule. The sample size thus obtained will result in a margin of error that is approximately equal to the specified value, cap E. And so let's look at another example. A poultry researcher is interested in estimating the total weight gain in 0 to 4 weeks for 1,000 chicks fed on a new ration. Now, obviously, to weigh each bird would be very time-consuming and tedious. Instead, a simple random sample of chicks will be selected and weighed, and an estimate of the total weight gain will be computed. The researcher found that in similar previous studies, the population variance of the weight gains has been around 36 grams, and so that is what we'll use as an approximation to sigma squared. So with that in mind, determine the number of chicks that must be sampled in order to estimate the total weight gain with a margin of error of no more than 1,000 grams. Okay, so again, we have a population of 1,000 chicks. From prior studies, it is believed that sigma squared for this population will be approximately 36 grams squared. We want to find the sample size, little n, such that the margin of error for estimating the total will be approximately 1,000 grams. So applying this formula, we see here that the sample size required would be around 126. Because we have a fractional value, 125.98, we're always going to go up to the next larger integer. And so if the researcher were to select a sample, a simple random sample of size 126, then as long as this estimate of the population variance, which is obtained from previous studies, as long as that is accurate, then the margin of error associated with the estimate that the researcher gets should be approximately 1,000 grams. All right, so those are the details on how to make inferences about a population total using data from a simple random sample. And in particular, we're talking about estimating the population total and constructing confidence intervals of the population total. We will continue on with the next topic in the next lecture video.